Here you are again. I don't know what day it is where you are, but where I'm at, it's Friday, and so this is Casual Friday. So welcome to Casual Friday. Last time, if you recall, I was talking about two types of operations you can do with rasters: zonal operations and neighborhood operations. And remember, with neighborhood operations, you have focal and block operations. Zones are kind of like custom-sized neighborhoods. There's one more processing type I need to cover, and that's called global. And in a global processing operation, the output value at each cell in a raster potentially depends upon the value of all the other cells in the raster. Okay, I've already talked about one of these, and that was distance, and Euclidean distance, kind of the equivalent of a vector buffer, is actually a global operation. So if you have one source cell that you're interested in and you do Euclidean distance, it's going to go through the entire raster and calculate the distance from that raster to the source cell. So that's a global operation. Here's an example. In this case we have two source cells, or source rasters. We have a source equivalent to a zone here, value 1, and another one to 2. And so what it does is it goes out and it calculates the distance from the nearest source cell to each cell in the raster. So in this case, let's look at source 2. At that cell, there's no distance to the source. If I go one cell over or one cell up, you can see the distance is 1. If I go at a diagonal using the Pythagorean theorem, the distance is going to be 1.4. You can see this is rounded off. So at some point, you cross over where the point where it's closer to one of the sources than the other source, and so it calculates as it goes which source cell the distance is from. Okay, remember that there's an allocation which will give you a raster that shows you which source cell is associated with each of those distances. There's also non-Euclidean distance, and what non-Euclidean distance is it says I'm going to take distance into account, but I'm also going to use some type of, let's call it a cost raster. So I'm going to consider not just the geometric distance between sources and cells, but the geometric distance times some type of cost between sources and cells. So it's a weighted distance. Here we have the same source raster. Here we have a cost raster. So for one reason or another, it's very expensive to cross this cell because this has a high cost. You can see the cost here is 7. And so the distance from this source to this cell is going to be higher than it would be if it were just distance. If it were just distance, the cost distance would be 1. But since there's a high cost there, you can see that we have 1, which is the spatial distance, but we also have 3.5, which is this cost distance. And so what this does is it allows you to weight a raster. And you can imagine this kind of being like a small equivalent to network modeling in the raster world, where let's say you had sources. This might be a road or a campground, and you might want to go to one spot or another, and you might have an elevation raster or a slope raster, and you could make a raster that represents the cost of climbing a hill or the cost of dense forest cover, and you could determine how far it is in terms of the cost of going from one cell to another as opposed to just the distance. So Euclidean distance is kind of like a regular buffer, but cost distance is kind of like a network. There are a bunch of distance operations. You can see how this works. The Euclideans are the basic distance measurements only. There are cost distances, which allow you to use a cost raster to help calculate things. And then there are these path distances. Those are like the raster equivalent to a network. Okay, what are some other tools we have? There's an set of extraction tools. You can extract individual or certain cells from a raster by a whole bunch of different methods. Okay, here's an example where we have a raster and we have a polygon, and we can say I only want the cells that are outside of the polygon, Or if you wanted to, you could also say, I only want the cells that are inside of a polygon. So if you were to take the cells only inside the polygon, that would be the equivalent to doing a vector clip on a raster data set. If you take the cells that are outside of the polygon, that's going to be the equivalent of a vector erase on a raster data set. So you can do inside or outside. Here's an extract by mask if you have a mask raster. And remember, you might calculate or create one of these using the raster calculator so that you had no data in the cells you weren't interested in and ones in the cells that you were interested in. You can extract by mask and take only the cells from the input that fall over the mask raster where there's no data. So you can see how that works. Generalization. Generalization, remember, is how much detail you're going to show. So if you have really small cells, you might say, I don't really need that level of detail. I want to generalize things to basically show me a lower level of detail. It's going to require less computation, less storage space. There's a bunch of generalization tools. Aggregate is one you might think of. Here we have a small celled raster, and we might want to aggregate that into larger cells because maybe we're going to do some type of overlays where one of our rasters has big cells and this source raster has small cells, but we're not going to get better data when we overlay a big and a small than we have in the biggest cell raster. So remember, the largest cell of your input when you're chaining operations together is probably going to be the limit on the data accuracy and precision in your output. So we don't need all this detail here. So we can aggregate this to larger cell size, and in this case we're going to use the aggregate tool and we're going to make it a 3 by 3 neighborhood. So we're going to go in this 3 by 3 neighborhood and we're going to take the maximum value in that neighborhood and we're going to store it in this new big cell. So you can see how you can aggregate things, go to larger cell sizes. This is the equivalent of what's called resampling for cell size resampling. And you can choose different, of course, methods to do your aggregation. You can do min, mean, majority, all of those different choices. Density. Density tools, there's 3 different flavors of density tools, and what they do is they take vector points or polylines and they spread the vector into a raster that is associated with the density of those points or polylines. So this illustration shows a bunch of points that have values. So our input would be a set of points, vector points that have values. The density tool will give us an output raster that represents the density associated with these distinct values that we have. So we go from vector points or polylines to a raster that way. 3 different flavors. We can go from points to a raster. We can go from lines to a raster. We can do what's called kernel density, which uses either lines or points, but it kind of smooths out the density calculation so that you get a smoother representation in your output raster. Okay, that was pretty much the basic stuff that you can do with raster data sets in terms of raster analysis. But it turns out that there are rasters that are associated with terrain, like elevation above mean sea level, that you can do some other things with that help you visualize and analyze the terrain. So next time I'm going to talk a little bit about terrain analysis, and that'll be the next video. So thanks for watching.